And we're back. Welcome back and happy Thursday. Today we'll continue on with some discussion of descriptive statistics. We will add to our discussion. But before that, a few administrative bits. The reading has changed by the 5th of February. Please make sure you have read Chapter 8, Section 8.3, which are pages 230 through 239. The reading pages have changed. They have been updated on the blackboard. Something has changed with the electronic version of the textbook. Homework number 1 is out and will be due a week from today, Thursday, the 4th of February. Please make sure at the usual 11:59 and 59 seconds, 1 second before midnight, please make sure you are managing your time. So, when we last left off, we talked about the sample mean, and we said that the sample mean is both unbiased and consistent. And this idea of unbiased says that on average, i.e. the expectation of the statistic, our estimator, theta hat, in this case the sample mean, if you compute the sample mean again and again and again, on average, it gives you exactly the unknown population parameter. We also looked at this idea of consistency, where consistency said a statistic, theta hat, an estimator, is consistent if the probability of sampling error goes to 0 as you increase the sampling size. So what that says is as long as the size of the sample set or the number of samples you take is large enough, that estimator, theta hat, the statistic, in this case the sample mean, diverges very rarely from the unknown population mean. And so if we increase the sample size, the estimator, our statistic, is less likely to differ from the population parameter. So let's take a look at the mean. We said the sample mean is unbiased and the sample mean is consistent. So what exactly does that mean about the mean? Well, it's fair. On average, it gives you what you want. It's a very good replacement for this unknown population parameter, the population mean, and it also gets better with experience. So it is a very good replacement or estimate for the hidden population mean. So recall from last semester when we talked about the central limit theorem as part of stochastic computing, we said that the sum of a large number of observations has a normal distribution. So here's the definition of the sample mean. The sample mean is just the sum of each of our n many measurements, our samples, we divide by n. And if we look at the numerator, well, certainly the numerator for the sample mean, the definition, has a sum. And because it has a sum or involves a sum, it adheres to the central limit theorem. And so from the central limit theorem, we said we compute a so-called z-score, which is a quintile from the standard normal distribution. And for the z-score, we said that you take your statistic, you subtract off from it the expectation of that statistic, the mean, and that centers the distribution, and then you divide by the standard deviation, which is the square root of the variance of that statistic. And that shrinks down your distribution so that it's of unit variance and also therefore unit standard deviation. And so for the sample mean, our statistic is x bar, and we're going to take a look at the expression for the z-score for our sample mean. So you take your statistic, your individual computations of your sample mean, you subtract off the expectation, which is mu, and then you divide by sigma upon radical n. And that sigma upon radical n is the square root of the variance of the sample mean, which is variance is sigma squared over n. So that's the square root of sigma squared over n in the denominator, or the standard deviation. Now, of course, the expectation of the sample denominator has a name, and that denominator is often called the standard error. And the standard error refers to the standard deviation of some quantity that itself was some statistic. And so in this particular case, when we compute the z-score, the distribution in question, x bar, is distributed as a normal. Yes, we said that. And the expectation of this sample mean of the statistic x bar is mu, so that's the mean, and the variance is sigma squared upon n. And so if you were to plot the distribution of measurements where each measurement is a value of x bar, well, the mean center is mu, and the square root of the variance, that's our radical, or sigma, over radical n. Okay, that's the standard deviation. And so that standard deviation for statistic x bar is called our standard error. And it's given a different name so that you'll know, oh, well, this particular standard deviation is the standard deviation of some statistic, some function calculated over the data. In particular, this function is x bar. So let's look at some notation. Here, when we say mu, Greek letter, mu, we refer to the population mean, x bar. That's the sample mean. Sigma is the so-called population standard deviation. That's standard deviation that we've been talking about associated with the population. S, on the other hand, is the sample standard deviation, the standard deviation computed over a set of samples. Sigma squared is the population variance. That's the variance we've been talking about all along. It's the variance associated with the population. And S squared is its counterpart over the sample. It's the sample variance computed over the samples. Okay, so let's take a look at the median. Now, the sample mean can be very sensitive to extreme observations, be they samples that are very small or samples that are very large. And so let's make another definition. What we're going to call an outlier is an extreme observation. So let's say if we have some set of samples, x1, x2, up to and including xn. And let's assume that we sorted them in non-decreasing order. So you have small values on this side, and you have larger values on the right-hand side. Now, of course, your outlier, x nu, can either be smaller than the smallest value or larger than the largest value. And we call an outlier an extreme observation if its value is much, much less than the smallest value or much, much greater than the largest value. So suppose if you have some numbers, and let's say these are ages, and you said somebody is like 31, 37, 42, and 50, for example, years old. Now, if you added an outlier on the low side, you would add a number like 1 or 2. If you add an outlier on the high side, you'd be adding a number like 100, for example. Now, of course, whenever you calculate the sample mean, well, you might get one value for x bar for the original data, but if you add another number and recalculate your x bar, your sample mean, if that number that you've incorporated, that new number you've included in your new calculation is an outlier, the mean is going to change very, very large amount. So let's look at a MATLAB example. We'll switch to MATLAB. I'll meet you in MATLAB. So we're here in MATLAB, and we're going to take a look at a demonstration concerning the brittleness of the sample mean to outliers. So we're going to start out with a population size of 10. So we're going to have 10 measurements, or 10 individuals, rather, comprising our group of individuals, and let's assume these are samples, which they are. So these samples, let's imagine they represented housing prices. So you sample some houses in an area, real estate, and you looked at the price of those houses, and you calculated the sample mean from it. Now, of course, let's assume on the low end houses are 200,000 in some locale, and on the high end houses are, say, 300,000 in some locale. So we take a random 10 many houses sampled, uniform at random in this interval between 200,000 and 300,000. So let's go ahead and do that. So we produce that sample, and we're going to call this our population of values. We have 281, 473, 290, 580. So it's just a number of values in between. So now we're going to calculate the sample mean from among this set of houses. So let's step, and we see that the sample mean is 262,000. Okay, that's the mean. But now what we're going to do is we're going to include an outlier. And so let's step through that, and we're going to compute the median. We haven't gotten to that yet, but we compute it nonetheless, and we'll talk about that a little bit in a few slides. So let's add an outlier to this population, and this outlier is going to be a house whose price is $5 million. And so it's an outlier on the left, on the right rather, much greater than all the other values. 5 million is much, much greater than 300,000. So if we add this outlier, now let's modify the population. Let's take our original population that we sampled, and let's add the outlier to that population. So step, let's look at the modified population. You can see there's the 5 million. Okay, so now what we're going to do is compute a new sample mean. We're going to sum the population, we're going to add the outlier to it, and then we're going to divide by the original population of 5 plus 1. So let's step here, and we find that our sample mean originally was 262,390, and the new sample mean is now 693,080. That's a lot bigger than the original sample mean. So by adding this outlier, we have changed or skewed the sample mean by a large amount. Okay, so let's go back to PowerPoint. I'll meet you back in PowerPoint. So we just demonstrated that the sample mean is sensitive to extreme observations. Now this is particularly damning, and imagine an application like heart measurements. You know, you have a smart watch and it's measuring your pulse or some aspect of your health status, and maybe it's taking these measurements 10 times a second or at some sampling rate. And let's say you decide you have to run across the street. So there's a brief moment of time when your heart rate goes way up, but that's not really indicative of what your typical or your actual heart rate is. So you have values included with your sample data that are much larger, the outliers on the high end. Now, of course, if it moves your sample mean, your mean heart rate, then it's going to be inaccurate relative and not a very true depiction of what your general heart rate typically should be. So an estimator whose value changes dramatically when new data arrives can't be very reliable. You can't rely on that because it's always jumping around, and you get the wrong idea about the central tendency of your set of samples, and therefore this estimator for your population will be wildly incorrect. So the median was created to alleviate or fix this problem. So let's take a look at what the median is. The median is the middle value versus the center of mass or balance point for a distribution. And the beauty of the median is that it does not change as much whenever your new data arrives. So let's take a look at the sample median. The sample median is noted as big M hat. It's really important to distinguish between the sample median and the so-called population median. Now the sample median is exceeded, i.e. other values are bigger than. The sample median, M hat, is exceeded by at most half of the observations. So if you have 10 observations, the sample median is exceeded by no more than 5. Half of your measurements or samples are bigger than the sample median, half of your samples, and it's preceded by at most half of the observations. That means no more than half the observations are smaller than. So the median is also called the middle order statistic. And an order statistic is nothing more than a position of an item when you sort your samples. So let's suppose you sort some samples, 1, 4, 7, 9, 11, in so-called non-decreasing order. Now, of course, we use the term non-decreasing instead of increasing because when you have non-decreasing order, that also accounts for values that have the same value, not just values that continue to get bigger. So let's take this list of samples, 1, 4, 7, 9, 11, in non-decreasing order. Now, the order statistic refers to the ICE value in that or some sorted order. And so the median is also called in the literature the middle order statistic because it's that order statistic corresponding to the middle, i.e. exceeded by at most half the observations and preceded by at most half the observations. So if we take this example, we have a total of 5 and half, well, we can't divide it precisely by half. 5 divided by 2 is 2.5, and this thing is preceded by at most 3. Okay, so it's preceded by 2, right? That satisfies at most 3, 1, and 4, and it's exceeded by at most 3. That's at most 3, 2, exceeded by 2. And so the 7 occupies the position in the middle, the so-called middle order statistic. I have 1, 2, 3, 4, 5 items, and their values are 1, 4, 7, 9, and 11. Well, the median is item number 3 in that list of 5 elements. So let's take a look at the case where the number of observations is even. Well, to compute the sample median, we still have that heuristic or the idea of exceeded by at most half and preceded by at most half of the observations. So if we have an even number, well, there's really no middle. In essence, there are two middles. We take the point that we synthesize, we calculate from the two middles. And so in this particular case, we have 4 items of value 1, 4, 7, and 9, and we put them in non-decreasing order. And here, if we take the sample median, well, we have 4 and 7 satisfying that sample median, at most 2 preceding, at most 2 exceeding, and we take the midpoint between the quote-unquote two middles, right? So here we have 4 and 7, and then we take the 4 and 7, we look at the midpoint. 4 plus 7 is 11, half of that is 5.5, so we calculate the median as being 5.5. And if you think about that value, 5.5, out of 4 items, half exceed it, that's items 7 and 9. Half precede it, that's items with value 1 and 4. So the procedure is a little different if the number of samples you have is odd or even. If it's odd, you have an actual value that is your middle order statistic or sample median. If it is odd, you have an actual value that is your sample median. If it is even, you synthesize it by taking or calculating the midpoint between the two middles. So there's also a population equivalent of the median called the population median. That's big M. And you notice here it's M with no hat, no caret above it, because it's the actual population parameter or value and not the sample value. It's not an estimator. And so the population median is the number or the value that is exceeded with a probability not bigger than 0.5. And it's also preceded by all the other values with a probability not bigger than 0.5. So said differently, for all of the values that a random variable can take on, the population median is that value M such that all those random variable values X being greater than M is no more than probability of 0.5, and all those values X less than M has a total probability of no more than 0.5. And so that means that M is that point for which there's a 50% chance, no greater than 50% chance a value is going to be bigger, and no greater than a 50% chance any value is going to be smaller. So that's the population median. Now, we can use the relationship between the mean and the median to characterize the shape of a distribution. Now, we're often concerned about the shape of a distribution because we're concerned or want an enterprise to think about how often we're going to see certain types of values. Values that are big, values that are small, values that are on less than the mean, values that are greater than the mean. And so in this first frame here on the right, we have what's referred to as a symmetric distribution. A symmetric distribution is one for which the population mean is equal to the population median. They are exactly coinciding. And symmetric distributions are typically symmetric about the center, about the mean. We also have, in this second frame, we have a right skewed distribution. And for a right skewed distribution, we have the population median is less than the population mean. And if we look at it, you'll notice here the highest part of the distribution is kind of mushed to the left. And if you think about what happens when you take the area under the curve, this portion kind of trailing off, it has a name, it's called the tail of the distribution. And when you have a tail, there's a lot of probability mass that exists in the tail. And so this particular distribution is going to prefer certain values with high probability, but there are a lot of values with low probability that if you add them all up, it adds up to quite a bit more. And so this skewed right distribution is going to prefer a lot of other values that it can choose from. So it tails off to the right. But there's higher probability associated with these values on this side of the population mean, on the left-hand side. So we have a tail that goes off to the right, and we have much more probability mass associated with values on the left-hand side of our population mean. We also have this other scenario on the frame on the right-hand side. It's called skewed left. Now, when it's skewed left, it's the opposite relationship between the population mean and the population median. It's skewed left if the population median is greater than the population mean. So here we see the population median to the right. Now, what does this mean? It means we have a tail that goes off to the left in the left-hand direction. And you'll notice here values that are greater than the population mean are going to have higher probability. They're going to show up more than the values that are smaller than the population mean. And so that tells you, the skewedness tells you what the preference is for values, how likely certain values are going to be preferred from this distribution. Because you have higher probability, well, when you're right skewed, your tail goes off to the right, and you prefer values that are less than the mean. When you're left skewed, the tail goes off to the left, and you prefer values, higher probability, that are to the right of the mean. And so the skewness refers to the direction of the tail. The tail goes off to the right, means you're right skewed. Tail goes off to the left, means you're left skewed. Okay. So how might we solve for the population median? Well, we can use the CDF in order to calculate that, the cumulative distribution function, which we talked about last semester. So let's rewrite these definitions that we had on the previous page. You have a population median. It's the value m, such that the probability of some value exceeding it is no more than 0.5, and the probability that a value is less than, it precedes it, is no more than 0.5. So let's take, for example, the uniform distribution. The uniform distribution is written as follows, and if you were to graph or plot the uniform distribution, it looks like the following. You have a value A, you have a value B, over which it's defined. Now, the uniform distribution is 0 for all values to the left of A, 0 for all values to the right of B, but for values in the interval between A and B, uniform has a probability density function of 1 over b minus a. Okay, so this is continuous because it's uncountably infinite, and the PDF is the following. The f of x, the probability, is 1 upon b minus a for those points in the interval between a and b, those values of x. Therefore, the CDF, cumulative distribution function, there's our expression for CDF. We take the integral from minus infinity to x, little x is the value, for our density function dx. And we note the CDF using capital F of x to jar your memory from last semester. So we would set up this integral. So here's our integral from minus infinity to x. We substitute in f of x, our density function for the uniform distribution, and then we perform that integral. Now, of course, that's the same as 1 over b minus a times the integral of 1 dx. Well, integral of 1 dx from minus infinity to x is just x. Now, this density function is only defined between a and b. And so from minus infinity to a, it's 0. And let me jar your memory here with the density function. Here's a, here's b, here's minus infinity. It has a value of 0, and then it goes up to a value of 1 over b minus a, and then we have some arbitrary value x, and we want to take the CDF, which is the area under the curve, from minus infinity to this x. And so when we do that, we are left with 1 over b minus a, integral from a to x, 1 dx. Well, this integral is just 1 over b minus a times x, and we evaluate that between the bounds a and x. So if we evaluate that, well, we plug it in, and we get the following. We say this PDF, that's its definition. We said that before, graphically. And the CDF, therefore, we just evaluate the definite integral from the indefinite integral by calculating this 1 over b minus a times x, substituting for x is the high value, minus that expression for x equals the low value. So that's 1 over b minus a times x minus a. All right. So there's our value for the CDF for all points that are less than a, it's 0. All points that are greater than b, it's 1. And the reason why it's 1 for all points x greater than b is because once you get to the right of b, you've already summed or calculated all the area under the curve for the entire distribution, which is a unit area because it's all of the probability mass. And so anywhere in between a and b, it's just x minus a over b minus a. And you can think of that expression as just the area of that rectangular region between a and x. And so if the height here is 1 over b minus a, that's the probability. If you want the area of this rectangle, that's height times width. The width is x minus a, that's this length, and then the height is 1 over b. So x minus a times 1 over b minus a, that's our x minus a over b minus a. And so this 1 over b minus a is going to be the height of the rectangle. So this is our CDF for the uniform distribution, and we have our density function as well. So now we can use the CDF along with the definition for what the population median is, and we can solve for it. So if the p of x greater than m is equal to 0.5, because 0.5 is the biggest that it can be, this means that the CDF evaluated at m is equal to 0.5, because the CDF is cumulative, and so we're looking at all those values that are bigger. So if we do that, we can substitute in using the CDF for this value m, set it equal to 0.5, and we can solve. So let's take a look at this. So we plug in, rather for this value p of x less than m, that would be our CDF. So we plug in for the CDF, this m. And so what is that? Well, we replace x with m. So we have m minus a over b minus a is 0.5. We do a little bit of algebra, and we get m is equal to a plus b over 2. Okay. Well, if you think about it, that is exactly what the median value is. If we have this uniform distribution, and here's our point A, here's our point B, this is our 1 over b minus a, defined between a and b. Well, the midpoint here in the population m is that point for which all values, if you add up all the probabilities, those that precede it, that's 50% of the probability mass, that's 0.5. Those that exceed it, that's 50% of the probability mass, that's also 0.5. So yeah, that makes intuitive sense as well. That is the population median. So now we know that this uniform distribution is symmetric, and from before, the expectation mu of the uniform distribution is 1/2 a plus b. And you see that the mean, mu, is exactly the same expression as the population median. And therefore, this uniform distribution is symmetric because it's true that mu is equal to m. So this tells us that there's symmetry in the uniform distribution, that it's a mirror reflection with respect to the mean. Now, of course, here's A, here's B, here's my probability density, 1 upon b minus a. This is what our uniform distribution looks like. Our mean is mu, and so if I draw this dotted line from mu, it's exactly a mirror reflection on both sides of mu, the shape of the distribution. So yes, it is in fact symmetric. So now we have a mechanical method that we can use to determine whether a distribution is symmetric, skewed left, or skewed right, where that skewness talks about lopsidedness to one side or the other. Which values does it prefer? If it's skewed left, it prefers values that are bigger. If it's skewed right, if it's skewed left, that means it prefers values that are bigger. If it's skewed right, that means it prefers values that are smaller, where the bigger probabilities are. Okay, so let's compute the sample median. Now, we're going to gather some number of observations, and we sort them in non-decreasing order, so this is a mechanization of it. If n is odd, then we're going to take the n plus 1 divided by second smallest observation as the median. If it's even, that's what we synthesize. We take the number that's between the n over second and n plus 2 over second smallest observation. So here we have the same numbers that we had before, and we sort them in non-decreasing order from smallest to biggest. And if we have two numbers that are the same, you notice here there's 82 and 82, right? The fact that you can have two numbers that are the same value, that's what makes it non-decreasing versus increasing. So we have 30 numbers, 3 rows of 10, and we have 30, so that means it's odd or even. So 30 is an even number, so we're going to take the n plus second, so 30 over 2 is 15, so we take the 10, 11, 12, 13, 14, 15, and n plus 2 over 2, so 30 plus 2 is 32, divide by 2, that's 16, so we take the 10, 11, 12, 13, 14, 15, 16. So we're going to take the 15th number, 42, and the 16th number, 43. So now we take the midpoint between the two. So that is the number in between 42 and 43. That's 42.5. And that's going to be our sample median. And so this is the example of how you calculate the sample median. So let's add some more notation. We, of course, have our population mean. We have our sample mean, x bar. We have our population standard deviation, our sample standard deviation, s. We have our population variance, sigma squared, and our sample variance, s squared. And we also have our population median, m, that we solved for, and our sample median that we calculated, big M hat. All right, so let's take a look at looking at. All right, so next time we'll focus on measurements of dispersion, how spread out your distribution is, and that's very useful in general for looking at the range of values that you might encounter. So that's all we have for this segment. We'll end there, and we'll pick back up on Tuesday. Have a great weekend, and I will see you Tuesday. Please make sure you're making progress on the homework.